This animation shows the core difference between going deep and spreading wide in a data structure. Instead of plunging straight down a single branch, breadth-first search, or BFS, moves horizontally, hitting every node on level 1 before dropping down to level 2, like a ripple spreading outward in a pond. When you see prompt keywords like level order, level by level, or shortest path in a tree, you are looking at a BFS problem. This diagram shows the engine behind that horizontal movement, the queue. It operates strictly on a first-in, first-out logic, exactly like waiting in line at a grocery store. To write this, we set up our main function and immediately handle our base case. If the root node is completely null, we return an empty array and move on. Managing breadth doesn't require tricky spatial navigation. It simply requires putting nodes in a queue and trusting the line to process them in the correct sequential order. This split screen shows our algorithms side by side with our data. We have our code editor on the left and our target binary tree with nodes 3, 9, 20, 15, and 7, along with an empty queue here on the right. We start by pushing our root node, the 3, directly into the queue. Then we open a while loop that will keep running as long as there is at least one node waiting in line. To process the tree level by level, we have to isolate the nodes currently in the queue from the children we are about to add. So we take a snapshot of the queue's length and store it in a variable. An inner loop runs exactly that many times. It pops the 3 out of the queue, saves it to our current level array, and pushes its left and right children, the 9 and 20, to the back of the line. Capturing that queue length snapshot before the inner loop starts prevents all the nodes from blending into one flat list. It ensures each level gets neatly packed into its own nested array. This diagram shows a pause timer. Take a second to look at the queue. Going into the second pass of our while loop, what will the snapshot size be, and which nodes will be processed? The snapshot size is 2. Our inner loop runs twice. It pops the 9, sees no children, and moves on. Then it pops the 20. Both values are recorded into a new nested array. While the 20 is being processed, its children, the 15 and 7, are pushed to the back of the queue. Because our inner loop limit was strictly set at 2, it stops processing before touching these new arrivals. That strict inner loop boundary isolates the middle of the tree. The algorithm stays on its current horizontal track and avoids diving deep into the next level. This animation shows the final loop iteration. The snapshot size is 2 again. The 15 and 7 are popped, placed in their own array, and since they have no children, this leaves the queue empty. The while loop breaks, giving us our final nested result. This graphic illustrates a 4-step blueprint. If you internalize these logical blocks, you won't need to memorize the exact syntax to build the algorithm. Step 1 checks the edge case, keeping empty inputs from breaking the code. Step 2 establishes the primary data structure by seeding a queue with your starting node. Step 3 opens the continuous traversal flow with a while loop and immediately takes a size snapshot. Step 4 uses that snapshot for an inner loop to process only the current level, queuing up the next level's children. Mastering this 4-step sequence gives you the heartbeat of the algorithm. You can now adapt this structure to solve any level order traversal problem, regardless of the programming language or the complexity of the tree.